Hello students, in the previous class discussion we discussed about how to get the analog transfer function with the help of the Butterworth polynomial for various orders. We discussed how to get the poles and how to locate those poles over unit circle, and which all the poles you have to consider, whether you have to consider the left half of the plane or the poles from right half of the plane. So we use only the poles which lies within the left half plane of the unit circle, and using those poles, you have to determine the polynomial, Butterworth polynomial, that is Bn of S, and 1 divided by that Bns gives you the analog filter transfer function Hij of S. And in the today's class we will discuss the design of low pass Butterworth filter. Again, it is the design of low pass Butterworth filter is nothing but determining the transfer function of the low pass Butterworth filter. And yesterday we have seen the magnitude response of the Butterworth filter in terms of its cutoff frequency as well as n. We had a transfer function, that is 1 divided by 1 plus omega c by omega raised to 2n whole raised to 1 divided by 2, that is the square root. So that is the magnitude response. So it is necessary to determine the first order of the filter n as well as the cutoff frequency, right? So what you have to determine, first we should know what is the order of the filter. N is the order of filter, and also we should calculate what is the cutoff frequency. Omega psi is the cutoff frequency, right? So in order to calculate these two, we should meet these two specifications. These are called as the frequency specification, right? These two frequency specification has to be met. So what are these specifications? They are explained with the help of the magnitude response here, right? And this omega p is called as passband frequency, and this omega s is known as the stop band frequency, right? And kp is known as the passband gain, and ks are known as a stop band gain, right? Both they are negative. So for all frequency less than or equal to omega p from here to here, right, this magnitude response in dB, that is 20 log of h of j omega, should be less than 0 and greater than kp. So that is the first specification. So we have to design a filter such a way that it should meet for all frequency less than or equal to omega p. What is the gain? The response, it should be less than 0 and greater than kp. And similarly for all the frequencies beyond this omega s, what should be the gain response? It should be less than or equal to ks. It should be less than or equal to ks. So these two specification has to be met in order to design the low pass Butterworth filter, right? So let us start our discussion with the magnitude response of low pass Butterworth filter. So that we saw in the yesterday class, that is h of j omega, its magnitude is given by 1 divided by, what is that expression, 1 plus omega by omega c raised to 2n and whole raised to 1 divided by 2, that is nothing but a square root, right? So since we have is 20 log of h j omega, right? So let us take the 20 log on both sides, right? So let me consider this one as equation number 1. So we'll take 20 log of hj omega is equal to 20 log. So if I take this denominator term to the numerator, so what it becomes? It becomes minus 20 log of 1 plus omega by omega c raised to 2n in raised to 1 divided by 2, right? So this raised to 1 by 2 becomes multiplication here. So minus 20 into 1 by 2 is minus 10 log of 1 plus omega by omega c raised to 2n, right? So now let us apply these specifications over here in order to get the order of the filter n as well as the cutoff frequency omega c. So we have to derive an expression for this n as well as omega c by making use of these two frequency specification, right? So I will write this equation in the next slide. So what is that? 20 log of h of j omega. So this is the magnitude response in dB, which is equal to minus 10 log of 1 plus omega by omega c raised to 2n, right? So now using the first specification for frequency omega is equal to omega p, what is the gain value? The gain value is equal to what? Yes, what is 20 log of h of j omega? Is that nothing but kp, right? So if I take this term as k, right, then this k becomes what? Kp. This k becomes what? Kp, because if you see here, at frequency omega is equal to omega p, what is the k value? K's value is nothing but kp. Similarly, at the frequency omega is equal to omega s, what is the value of k? K is nothing but this 20 log of hj omega. So this value is equal to what? Ks, right? So that substitution I will make here, k is equal to kp, right? So this one I will write kp here. This is nothing but kp is equal to minus 10 log of 1 plus, what is omega? Omega is nothing but omega p, and this omega c I will keep as it is, that is 2 raised to n, right? So now let us simplify this one, right? So how to simplify? First we'll take minus 10 this side. So what it will become? It becomes what? Yes, minus kp divided by 10, kp divided by 10. Yes, if I take log this side, what it becomes? It becomes nt log. Nt log means it is 10 raised to minus kp by 2 is equal to divided by 10. Then if I take 1 this side, this becomes what? Minus 1, right? This becomes what? Minus 1, that is equal to omega p divided by omega c raised to 2n. Is that clear? Right? Next, so this is considered as equation number 2. Similarly, we will apply the second specification. What is that? For omega is equal to omega s, what is the value of k? K is nothing but ks, right? So this becomes ks minus 10 log 1 plus omega s by omega c raised to 2n. In a similar way, if I simplify this one in the form of this, so what you will get? You will get 10 raised to, that is nt log 10 raised to minus ks by 10 minus 1 is equal to omega s by omega c raised to 2n. So let me take as equation number 3, right? So now let us divide the equation 2 by equation 3, right? So by dividing equation 2 by equation 3, what we will get? Omega p by omega c raised to 2n divided by omega s by omega c raised to 2n is equal to 10th power 10 raised to minus kp by 10 minus kp by 10 minus 1 divided by 10 raised to minus ks by 10 minus 1, right? So here this omega c and omega c will get cancelled. So what you will get? You will get omega p divided by omega s raised to 2n, that is equal to 10 raised to minus, what is 1 divided by 10? That is nothing but 0.1 times kp minus 1 divided by, please you have to be very careful while writing minus 1 here. It is not minus 0.1 kp minus 1, it is 10 raised to minus 0.1 kp minus 1, similarly divided by 10 raised to minus 0.1 ks, and here it is minus 1, right? So now what you have to do is next, right? Let us take the log on both sides here. Let us take the log on both sides, because we have to separate this n term from this power, right? And for that, so let us take the logarithm on both the sides, right? So after taking logarithm, what you will get? You will get 2n log of, using the property omega p divided by omega s is equal to log of 10 raised to minus 0.1 kp minus 1 divided by 10 raised to minus 0.1 ks minus 1, right? Now what we want is, we want n here, right? So except this n, will shift all the remaining terms to the right side, so that you will get an expression for n is equal to log of 10 raised to minus 0.1 kp minus 1 divided by 10 raised to minus 0.1 ks minus 1 divided by 2 times log of omega p divided by omega s. So this is the expression for order of the filter, right? Where kp will be given, ks will be given, omega p and omega s are given, right? And this omega p and omega s, they are analog specifications, right? Even in the problem statement, if the digital specifications are given, using frequency warping, we have to convert the digital frequency specifications into what? The analog frequency specifications, right? So this is about the order of the filter n, right? And then next we'll calculate what is the cutoff frequency, right? So here we have two equations, equation number 2 and equation number 3, right? You can use any one of the equation to solve for the cutoff frequency, right? So I will use the second equation first. What is that? Omega p divided by omega c raised to 2n is equal to yes, 2n is equal to 10 raised to minus kp divided by 10 minus 1, right? So what we want is omega c we want, right? Again by taking logarithm on both the side, or else, right, you can shift this 2 in this side, right? So I will multiply omega p by omega c, 2n is there. On both sides I will multiply, power I will multiply by what? 1 divided by 2n, and the power of this also I will multiply by what? 1 divided by 2n minus, sorry, kp divided by 10 minus 1, here it is 1 divided by 2n. So this 2n and this 2n will get cancelled. So what you will get? Omega p by omega c is equal to 10 raised to minus kp divided by 10 minus 1 into 1 divided by 2n, right? So what we want? We want the cutoff frequency. So we will take this omega c this side and this term this side. So omega c is equal to omega p divided by 10 raised to minus kp divided by 10 minus 1 raised to 1 divided by 2n, right? So this is one equation you can use whenever omega p and kp are given. If in the problem statement, if you have only data like omega s and ks, then you can use the alternative equation for omega c, that is omega s divided by 10 raised to minus ks divided by 10 minus 1 raised to 1 divided by 2n. This is another equation to calculate the cutoff frequency. Is that clear? Either you can use the first one or second one depending upon the specifications given in the problem statement, right? So in this derivation, right, so it is about the design of low pass Butterworth filter, right? Because to calculate HA of S, right, we need the Butterworth polynomial, right, that is Bn of S. And what is this Bn of S? The Butterworth polynomial is given by, yes, it is left half plane, the folds of left half plane, right? What is this Sk? This Sk is nothing but what? The Sk is nothing but force which is given by 1 with a phase angle of theta k, right? And what is this theta k? Theta k is nothing but pi k divided by n plus 2 pi divided by n plus pi by 2. Understood? Where we require n here as well as k here. So k depends upon 0, 1 up to 2n minus 1. So what we require is, we require the order of filter n, right? So that n is calculated by the equation which we derived in this video. Is that clear? Right? So this is about the design of the low pass Butterworth filter with order of the filter n as well as the cutoff frequency omega c. In the next video, and one more important thing I forgotten to mention is, this derivation is very important for the examination of point of view for 8 to 10 marks, right? So they will directly ask, derive an expression for the order of the filter n and the cutoff frequency omega c for Butterworth low pass filter or low pass Butterworth filter, right? In the next video, so we'll discuss a very important numerical example where you are supposed to calculate the order of the filter, cutoff frequency, and then the analog transfer function. That is nothing but the design of filter, analog filter. Thank you.